Millions of years had passed since the first dinosaurs emerged from the shadows of extinction. They now ruled the land, but the land itself was changing beneath their feet. Pangaea, the colossal supercontinent that had once stretched from pole to pole, was breaking apart. The ancient unity of Earth's land masses was ending. Tectonic forces, slow but unstoppable, were pulling continents in every direction. And with every crack, rift, and shift, the world was being rewritten, not just geologically, but biologically. This was a shattered Pangaea, and its breaking would shape the future of life on Earth. At the heart of this transformation were the forces beneath the Earth's crust. Heat and pressure built over tens of millions of years, warping and fracturing the rigid plates that held the continents together. Magma surged upward through deep fissures, forming vast volcanic provinces that spilled lava across hundreds of thousands of square kilometers. The Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history, left behind scars still visible today. Its eruptions marked the beginning of the end for Pangaea and the dawn of the Jurassic. The supercontinent began to tear along what would eventually become the Atlantic Ocean. North America drifted westward, Africa and South America pulled apart, and the Tethys Sea expanded between the northern and southern landmasses. This slow continental drift, measured in centimeters per year, created vast rift valleys, new coastlines, and isolated inland seas. Land that had once been unified and stable was now fragmented, with oceans and deserts emerging between what were once neighboring ecosystems. The climate responded. As Pangaea broke apart, the global climate began to shift from extreme and seasonal to more varied and regional. Air masses flowed differently. Rain fell where it had once failed to reach. Deserts began to shrink. New monsoon systems developed near the coasts. Lush tropical forests replaced dry interiors. Humidity rose in many regions, feeding the growth of plant life and opening up new habitats for herbivores and their predators. Ecosystems diversified, and so did the dinosaurs within them. With the fragmentation of land came the fragmentation of populations. Species once connected across continents became isolated. This geographic isolation was a powerful force in evolution. Populations adapted to their new surroundings, evolving separately from their cousins on other landmasses. Over time, new species formed, each uniquely suited to their region. This is how nature builds variety, not in stillness, but in movement, not in sameness, but in separation. In what is now North America, new sauropods began to evolve. Long-necked giants like Apatosaurus and Camarasaurus would one day dominate the open plains. In Africa, a different branch of sauropods, like Volcanodon, emerged. In Asia, early stegosaurs and armored species began to take form. And across the spreading landmasses, theropods adapted into countless shapes, some growing larger, others more agile, and still others more intelligent. This explosion of diversity was directly tied to the geography of a world breaking itself apart. The oceans, too, were changing. As the continents drifted, shallow seas flooded inland, creating vast coastal habitats teeming with life. Coral reefs expanded. New marine reptiles emerged to take advantage of the growing abundance. Plesiosaurs glided through the water with long necks and flippered limbs. Ichthyosaurs, shaped like sleek fish, darted through schools of prey. The sea became a new frontier, and evolution answered the call. Volcanic activity continued to shape the Earth. Lava fields blanketed huge areas. Ash and gases filled the skies, sometimes cooling the planet temporarily, other times warming it. These climatic fluctuations, while devastating in the short term, fueled evolutionary pressure. Species had to adapt quickly or disappear. Those that could not handle the changing temperatures, shifting coastlines, or unpredictable rainfall patterns were lost to time. Those that could, the adaptable, the mobile, the efficient, flourished. The breakup of Pangaea also reshaped migration. Dinosaurs that once traveled across a single continent now faced physical barriers. Rivers widened, seas emerged, mountain ranges rose from tectonic collisions. Migration routes became more complex and, in some cases, impossible. This limited gene flow between populations, further accelerating speciation. Local ecosystems became more distinct. Predators evolved to hunt specific prey. Herbivores adapted to regional plant life. Over time, the biosphere became a mosaic of highly specialized creatures. Not all changes were dramatic. Some were subtle, unfolding over millions of years, but the direction was clear. Unity was giving way to diversity. The old world of Pangaea, flat, hot, uniform, was being replaced by a new world of complexity. With it came the opportunity for new behaviors, new relationships, new ways of living. This fragmentation even influenced behavior. Herding, for example, became more common as predators grew larger and more coordinated. In fragmented landscapes, safety in numbers offered protection against ambush. Nesting behaviors began to shift as well, with evidence suggesting more communal nesting sites and perhaps even primitive forms of parental care. As environments became more diverse, so did social structures. And while the dinosaurs rose in power and variety, small mammals continued to evolve quietly in the underbrush. They scurried through ferns and beneath roots, avoiding the giants above, though they would not dominate for many millions of years. Their evolutionary foundation was being shaped in this same dynamic world. The shattered Pangaea affected all life, great and small. As the Jurassic period began, Earth had become a planet of motion and transformation. Continents drifted steadily toward their modern positions. Climates cooled and warmed, forests expanded and contracted, mountains rose, seas deepened, and everywhere life followed. Dinosaurs walked new paths across strange new lands, each one a branch of a tree that would grow to fill every niche available. What had once been a single colossal landmass was now a collection of evolving worlds, each with its own rhythm and rules. This was the legacy of a shattered Pangaea, not destruction, but diversification, not collapse, but creation. And in the cracks of this broken continent, life found new ways to thrive. They rose slowly, silently, but with purpose. Towering shadows drifting across floodplains, necks reaching above the treetops, tails sweeping through ancient ferns, their feet pressed deep into the mud, shaping the land with every step. They were the sauropods, the largest creatures to ever walk the earth. But their rise was not sudden. It was the result of millions of years of adaptation, driven by hunger, movement, and the relentless pull of evolution. They were not born giants, they became giants. The early Jurassic was a world of opportunity. With Pangaea breaking apart and climates becoming more humid and stable, vast new ecosystems opened up. Dense forests, river deltas, and coastal plains created a mosaic of plant-rich environments. For a creature that fed constantly, this was paradise. The first true sauropods emerged from their smaller ancestors, the sauropodomorphs, and began to explore this expanding buffet. Volcanodon was among the earliest. Though modest by later standards, it displayed the foundational traits of sauropods: column-like legs, an elongated neck, and a shift toward obligate quadrupedalism. It was no longer built to rise on two legs like its ancestors. Its size demanded a new posture. Walking on all fours provided stability, massive limbs supported its growing weight, and its neck gave it access to a wide feeding range without the need to move its entire body. This was the beginning of a revolution in herbivory. The neck was a marvel of biological engineering. Flexible, powerful, and often longer than the rest of the body, it allowed sauropods to feed high in the canopy or sweep low across the ground, depending on the species. It meant less energy spent walking, more energy gained from feeding. And unlike giraffes, whose necks are constrained by blood pressure and vertebral count, sauropods developed additional cervical vertebrae and air-filled bones that reduced weight without sacrificing strength. Their entire bodies were designed around efficiency and scale. Sauropods also possessed an unusually effective respiratory system. Like birds, their lungs were connected to a system of air sacs that extended into the bones. This allowed for a unidirectional flow of air, improving oxygen exchange and supporting the demands of such massive bodies. Their metabolism, while still debated, likely balanced energy conservation with growth, allowing juveniles to reach immense sizes in relatively short spans of time. Rapid growth meant less time vulnerable to predators. It also meant greater feeding demands, which these landscapes could now provide. They did not feed alone. Sauropods lived and moved in herds, sometimes dozens or even hundreds strong. Fossilized trackways in Argentina, Portugal, and the United States reveal parallel footprints, consistent stride lengths, and spacing that suggests coordinated movement. Herding offered protection for the young, and perhaps even social bonds among adults. Their movements shaped the land. They trampled ferns into open meadows. Their droppings fertilized the soil. They were ecosystem engineers long before the term existed. And predators took notice. The rise of sauropods created a ripple effect in evolution. To hunt something so massive, carnivores had to adapt. Early theropods began to grow larger, stronger, more coordinated. But even at their most powerful, few predators dared take on a healthy adult sauropod. Their size alone was defense. It was the juveniles, the sick, the isolated that drew attention. And so sauropods developed strategies to protect their own: tight herding, coordinated movement, and perhaps even vocal communication. They spread across the world. Wherever there was plant life and room to move, sauropods arrived. Mamenchisaurus appeared in Asia, with a neck stretching over 15 meters. Cetiosaurus, the so-called whale lizard, lived in the rivers and floodplains of Europe. In Africa, Jobaria wandered the open plains. South America hosted a growing variety of forms, including the early ancestors of the titanosaurs, who would one day dominate the Cretaceous. Their success was not due to aggression or speed, but persistence. They did not need to hunt. They needed only to feed and grow. They were creatures of rhythm. They followed seasonal rains, moving between dry and wet habitats. They remembered water sources and returned to them year after year. They migrated in search of fresh vegetation, carving ancient paths into the land. Their lives were shaped by slow cycles of growth, of movement, of reproduction. A single individual might live for decades, watching the world shift around them. Yet for all their size and power, they were vulnerable. Eggs laid in shallow nests could be destroyed by floods or trampled by other animals. Juveniles, even the size of cows, were still targets. A broken leg could mean death. A drought could force a herd into starvation. Being large came with a cost. They survived by minimizing risk, not eliminating it. Still, they endured. Their bones, scattered across the globe, tell a story of quiet dominance, of animals who did not need to chase or flee, who shaped the world simply by existing. They were the living pulse of the Jurassic landscape, steady and unrelenting, The rise of sauropods marked a turning point in the age of dinosaurs. It proved that size could be a strategy, that slow and steady could triumph over fast and fierce. It opened the door for later giants, the Seismosaurus, the Argentinosaurus, the brachiosaurus, creatures so immense they defied imagination. But it began here, with the early steps of a few long-necked grazers in a world freshly broken and blooming with life. In the shattered remnants of Pangaea, the sauropods rose, and the world rose with them. As the herds of sauropods grew larger and more dominant, their presence rewrote the laws of survival. They reshaped the land, drew lines of migration across entire continents, and transformed once diverse habitats into vast feeding grounds. But in their shadow, something else was evolving, something leaner, sharper, faster. For every giant that grazed in the open, a predator waited nearby, adapting, refining, learning. This was the era of the new hunters, a rising class of theropods that would redefine what it meant to kill in the Jurassic world. The decline of the old apex predators had left a void. The Rauisuchians, once the top predators of the Triassic, had vanished. Their downfall came not from battle, but from time and change. Their massive bodies, slow development, and limited adaptability had doomed them when the world shifted. And into that opening, theropods had already begun to step. Now, in the early Jurassic, they took control. Among the first to emerge was Dilophosaurus. With its slender build, long legs, and distinctive twin crests atop its skull, it was a predator made for speed and agility. It measured over 6 meters in length, but weighed far less than its size might suggest. Its body was hollow-boned and lightweight. Its jaws were long and flexible, lined with sharp, curved teeth capable of slicing flesh. Dilophosaurus was not a brute force killer. It was a strategist. It hunted with precision, relying on stealth, speed, and timing. Dilophosaurus roamed river valleys, forests, and floodplains. It may have hunted in pairs or small groups, coordinating to bring down larger prey. It likely used ambush tactics, striking from cover and retreating quickly if needed. Its speed allowed it to test its prey, to probe for weakness without committing to a dangerous fight. It fed on early ornithischians, young sauropodomorphs, and perhaps even scavenged when opportunity struck. It was an opportunist, not a specialist, and that was its strength. The success of predators like Dilophosaurus was rooted not in size, but in adaptability. Their bodies were modular, able to evolve rapidly in response to environmental pressures. Longer limbs for faster running, sharper teeth for more efficient killing, stronger tails for balance, forward-facing eyes for better depth perception. These traits could shift within generations, fine-tuned by the relentless forces of natural selection. The result was a family of predators that could take on any role the ecosystem demanded. As sauropods grew larger, so too did the challenge of hunting them. Few predators could face an adult head-on. Instead, the new hunters focused on the young, the old, and the sick. They followed herds from a distance, watching for stragglers. They learned the rhythms of migration. They learned the vulnerability of nesting grounds. Fossil sites suggest that predators congregated near breeding areas, waiting for eggs to be laid or hatchlings to emerge. They were not just killers, they were observers, patient, calculating. Some of these theropods began to show signs of social behavior. Fossil trackways in China and the western United States reveal parallel movement patterns, multiple individuals traveling together at matching speeds. Whether this was true pack hunting or simply a temporary alliance is unclear. But it points to an emerging intelligence. These were no longer solitary ambush predators. They were beginning to think, to interact, to coordinate. Their intelligence was supported by a growing brain size relative to body mass. Theropods developed increasingly complex sensory systems. They could see farther, hear better, smell more acutely. Their skulls housed large optic lobes, suggesting visual acuity. Their inner ears were sensitive to balance and movement. They became more aware of their surroundings, more capable of responding to subtle changes in prey behavior or terrain. They were not just reacting to the world, they were reading it. Competition among these new hunters was intense. Multiple theropod species often shared the same habitat. Some evolved to be generalists, feeding on a wide range of prey. Others specialized, focusing on fish, small reptiles, or even carrion. Their bodies reflected these choices. Some had long, narrow jaws like modern crocodiles. Others had stout skulls and powerful necks for delivering crushing bites. The diversity of form mirrored the diversity of strategy. As the Jurassic progressed, this diversity only increased. New species emerged across the globe, each adapting to their own environment. In Africa, Megalosaurus began to rise. In Asia, early ancestors of the later allosaurs took shape. North America saw the spread of larger, more robust theropods. And throughout these regions, the arms race between predator and prey accelerated. This escalation shaped every aspect of life. Herbivores began to evolve defensive adaptations: thicker skin, tail clubs, herd behavior, nesting in guarded sites. Even changes in reproductive strategy, laying more eggs more often, may have been a response to predation pressure. The presence of intelligent, coordinated hunters forced prey species to evolve not just physically, but behaviorally. The impact of these predators went beyond biology. They altered the flow of energy in the ecosystem. Their kills fed not just themselves, but scavengers, insects, small mammals, even other dinosaurs. Their presence regulated herbivore populations, preventing overgrazing. They drove movement, kept herds mobile, pushed species into new territories. They were not just consumers, they were catalysts. And through it all, they kept changing. The theropod body plan was not static. It continued to evolve, becoming more efficient, more refined. From this lineage would one day emerge the giants of the late Jurassic: Allosaurus, Ceratosaurus, and eventually Tyrannosaurus. And further still, the small feathered hunters that would give rise to birds. It all began here, in the early Jurassic, in the age of the new hunters. They did not roar with brute strength. They whispered through the underbrush. They waited. They watched. And when the moment was right, they struck. Their rise was quiet, precise, and unstoppable. Beneath the towering necks of sauropods and the stalking gaze of theropods, life began from the ground up. The true architects of the Jurassic world were not the creatures that roared or ran, but the plants that swayed gently in the wind, caught the sun, and fed the entire web of life. Without them, the dinosaurs would never have thrived. And during the early to mid-Jurassic, the landscape was dominated by two primary plant kingdoms: fern prairies and conifer forests. Together, they created the stage upon which the dinosaur empire expanded. The Earth during this time was warmer and more humid than today. With Pangaea still drifting apart and volcanic activity constantly reshaping the terrain, the climate nurtured widespread rainfall across many regions. This moisture allowed plant life to thrive in ways unseen since the Carboniferous. And while flowering plants had not yet evolved, their ancestors had built a green empire of their own, one that was tougher, older, and deeply intertwined with dinosaur evolution. The open lowlands, floodplains, and valleys were covered in thick mats of ferns. These plants had no flowers, no seeds, and no true wood. They reproduced by spores and spread rapidly wherever moisture was abundant. Their leaves, or fronds, stretched across the ground in vast, tangled networks. They carpeted the soil between trees, filled the spaces beneath canopy gaps, and rebounded quickly after floods or fires. These were the fern prairies, sprawling fields of dense green life, feeding countless herbivores with every bite. The ferns were the staple diet for many early plant-eating dinosaurs. Stegosaurs, early ornithopods, and juvenile sauropods grazed on them constantly. Their leaves were low to the ground, easy to harvest, and grew back fast after being trampled or consumed. And because they grew in thick patches, ferns allowed herds to stay in one place for longer without exhausting their food supply. They were not nutritious by modern standards, but for creatures with massive stomachs and slow digestion, volume mattered more than quality. These prairies also played a key role in shaping movement and behavior. Herds would follow the seasonal growth of ferns, returning to fertile valleys after monsoons passed. Predators followed the herds. Scavengers followed the predators. And everywhere, the ferns kept growing, quietly driving the rhythm of survival. But not all of the Jurassic was open space. Rising above the ferns stood another kingdom, the forests of conifers. These trees, ancestors of pines, redwoods, and cypresses, dominated the uplands, the hillsides, and the mountainous regions. They reached incredible heights, with trunks thick enough to support dozens of meters of vertical growth. Their branches stretched outward like spoked wheels, catching sunlight and shading the forest floor below. Their needles were tough and waxy, designed to conserve moisture and resist grazing. They were not easy food, but for the largest dinosaurs, they were essential. Sauropods evolved long necks not only to feed high, but to reach deep into these conifer canopies. Some species browsed the outer branches, stripping needles with comb-like teeth. Others fed on cones, rich in nutrients and easier to digest. Their sheer height allowed them to exploit a food source unreachable to other herbivores. And in doing so, they created layers within the ecosystem, feeding zones separated by elevation. Stegosaurs and small ornithischians grazed low on the ferns. Iguanodonts browsed mid-height shrubs, and sauropods harvested the trees. Beneath the canopy, the forests were alive with more than just dinosaurs. Ancient insects swarmed the undergrowth. Millipedes and beetles fed on decomposing needles. Early mammals darted through root systems and rotting logs, feeding at night and hiding during the day. Amphibians lingered near streams, while pterosaurs nested in high branches or on rocky ledges nearby. The forest was not just a backdrop. It was a complex, layered system of life, bound together by the trees themselves. Fire was a regular part of this world. Lightning strikes ignited dry undergrowth during seasonal droughts. The fires cleared old growth, released nutrients, and opened sunlight to the forest floor ferns. Ever opportunistic, regrew quickly. Conifers, with their thick bark and resinous cones, were built to survive. Some species even required fire to open their cones and release seeds. This cycle of fire and renewal shaped the evolution of both plants and animals. Creatures that could move fast or burrow deep had better chances. Dinosaurs learned to migrate or wait. Life adapted to the burn. Plant distribution followed geography. In coastal regions where soils were sandy and salty, only the hardiest species grew. Inland floodplains, fed by sediment from rivers, supported lush fern prairies and small groves. Volcanic uplands, rich in minerals but prone to erosion, fostered dense forests of conifers, ginkgos, and cycads. Wherever the land allowed, the plants took root. And wherever the plants grew, dinosaurs followed. The plants also played a role in climate regulation. Vast forests absorbed carbon dioxide and released oxygen. Their roots stabilized soil. Their presence helped trap moisture in ecosystems. And as they died, decomposed, and fossilized, they helped form the layers of rock and carbon that would one day record this world in stone. The fossil record preserves their legacy. Entire fern mats have been fossilized in fine-grained mudstone. Upright tree trunks, petrified in place, still bear the marks of ancient bark. Fossil pollen grains, viewed under microscopes, reveal the spread of plant species across ancient continents. Even dinosaur coprolites, fossilized droppings, contain fragments of chewed ferns and broken needles, offering a direct link between plant and animal. In many ways, the rise of dinosaurs was only possible because of the rise of these plants. The vast herds of the Jurassic did not feed on air. They fed on ferns and conifers, on cycads and ginkgos, on the quiet rooted life that turned sunlight into growth. These plants were the foundation of the food web, the architects of ecosystems, the silent forces beneath the roar. Fern prairies and conifer forests were not just scenery, they were survival. And as long as they grew, the age of dinosaurs could continue. In the age of dinosaurs, survival depended on more than size, speed, or strength. It also depended on strategy, on behavior shaped not by instinct alone, but by learning, communication, and adaptation. The Jurassic world was not just a battleground of bodies, it was a theater of evolving minds. And in the shifting landscapes of this time, dinosaurs began to change not just in form, but in thought. Behavioral evolution is difficult to trace in fossils. Bones tell us where muscles once attached, how joints moved, how creatures walked or ran. But behavior, the things dinosaurs did, how they reacted, how they lived and raised their young, is written in traces, in footprints, in nesting grounds, in rare glimpses of moments frozen in time. And these traces suggest that as dinosaurs diversified, their behaviors became more complex. One of the most critical changes was the evolution of herding and group dynamics. Fossilized trackways, preserved in riverbeds and floodplains, reveal patterns of coordinated movement. Dozens of individuals moving in the same direction, at the same pace, with footprints overlapping in regular intervals. This wasn't chaos, it was organized motion, evidence of herds. Sauropods, stegosaurs, and some ornithopods likely moved in groups for safety and access to resources. Young dinosaurs would have been especially vulnerable to predators. Herds offered protection. The more eyes watching, the less chance of surprise. The more bodies in motion, the harder it became for a predator to isolate a single target. For a young dinosaur, being part of a group could mean the difference between life and death. But group behavior may have extended beyond movement. Nesting grounds discovered in places like Argentina and Mongolia show evidence of communal egg-laying. Dozens of nests arranged in clusters, each containing carefully laid eggs. Some show signs of repeated use across years, with new nests dug above old ones. These weren't random deposits, they were colonies. And they suggest that some dinosaurs returned to the same sites generation after generation, driven by memory, tradition, or seasonal cycles. Parental care also appears to have evolved in some species. Fossils of adults found near nests, or even positioned protectively over eggs, hint at the possibility of guardianship. Though it's still debated how extensive this care was, the patterns suggest more than abandonment. In species like Maiasaura, which would appear much later in the Cretaceous, fossil evidence clearly shows adults feeding and tending to hatchlings. If this behavior had its roots in the Jurassic, it marks a major evolutionary milestone, the emergence of family dynamics in reptiles. Predators were evolving behaviors of their own. Theropods like Dilophosaurus and early megalosaurs may have hunted in coordinated groups, especially when targeting larger prey. Fossilized footprints hint at multiple individuals moving together, possibly in pursuit. Coordinated hunting required communication, visual cues, body language, perhaps even vocalizations. It wasn't enough to be fast or strong. They had to be aware, reactive, and sometimes even cooperative. Communication itself was likely evolving across species. Vocal cords don't fossilize, but the shape of skulls and nasal passages gives clues to sound production. Crests and horns may have amplified calls or been used for low-frequency rumbling. Bright color patterns displayed on skin or feathers in later species could have played a role in visual signaling, attracting mates, warning rivals, or identifying members of a group. Social animals benefit from the ability to be seen and heard, and dinosaurs were becoming more social than ever before. Territorial behavior also emerged as ecosystems grew more crowded. Trackways and fossil distributions suggest that certain species kept to specific regions. Predator-prey relationships developed within defined zones. Herbivores followed seasonal plant growth but returned to known areas. Competition for resources, water, food, nesting sites, led to the development of boundaries, of dominance displays, of conflict and avoidance. Some dinosaurs likely used size or sound to warn rivals before engaging. Others may have resorted to physical combat, locking horns or swinging tails in shows of strength. Even sleep patterns may have evolved in response to environmental pressures. Small dinosaurs living in regions with large predators may have adopted nocturnal behaviors, foraging under cover of darkness. Fossilized eye sockets can reveal the relative size of optic lobes and night vision capacity. Some species were built for the daylight, others for the twilight. Intelligence, though hard to quantify, was advancing. Theropods in particular began to show signs of higher brain-to-body ratios. This doesn't mean they were self-aware or capable of abstract thought, but it does suggest better coordination, faster learning, and more complex problem-solving. These traits would later culminate in the highly intelligent raptors of the Cretaceous, but their roots may have stretched back to this Jurassic experimentation. Across species, across continents, dinosaurs were testing new strategies. They were not static creatures locked in primal routines. They were evolving behaviors shaped by experience, environment, and interaction. Their minds, like their bodies, were being sculpted by survival. The changing world demanded more than raw power. It demanded adaptability, cooperation, awareness. And the dinosaurs answered. They began to form communities. They began to protect their young. They began to learn, in their own way, how to live not just as individuals, but as members of a greater whole. In the silence of nesting grounds, in the long trails carved by herds, in the cautious steps of predators circling their prey, we see more than survival. We see evolution at work, not just in shape or size, but in thought. And that evolution would carry forward, shaping the creatures that would someday inherit the Earth. The Jurassic world was not gentle. It was a land of contrast, of opposites living side by side. Scorching days followed by freezing nights. Lush forests shadowed by desolate plains. Quiet nesting grounds interrupted by violent storms. To live in this era was to endure a planet constantly shifting between comfort and chaos. The animals that survived did so not because the world was easy, but because they adapted to its extremes. As Pangaea continued to break apart, the geography of the planet changed dramatically. Massive rift valleys formed, separating once connected ecosystems. The creation of new coastlines brought in warm, moist air that fed thick clouds and long seasonal rains. Vast inland deserts still dominated central regions, but now they were surrounded by belts of tropical vegetation. In the space of a few hundred kilometers, the climate could swing from arid to wet, from hostile to abundant. These regional climates were the direct result of continental drift, ocean circulation changes, and constant volcanic activity. The land itself was a patchwork of extremes. Volcanoes were one of the defining forces of this time. Even after the initial pulse of eruptions that shattered Pangaea, volcanic activity remained constant. Magma seeped up through rifts, forming new mountain ranges and blanketing the ground in ash. Lava flows destroyed forests, but left behind fertile ground for new growth. The skies often turned orange and red, not from sunsets, but from smoke and suspended particles. Dinosaurs living near these active zones had to migrate often, abandoning nesting grounds or food sources with little warning. Many never returned. Yet, where death struck, life often rebounded stronger. These eruptions also affected the global climate. Each major volcanic event released clouds of ash and sulfur dioxide into the atmosphere. Sunlight was blocked. Temperatures dropped for years at a time. This temporary cooling, known as volcanic winter, hit tropical and temperate ecosystems hard. Some species adapted by slowing their metabolism or altering reproductive timing. Others simply vanished. In these cooler years, only the most resilient creatures endured. But the cold never lasted. When the ash settled, greenhouse gases from the same eruptions took over. Carbon dioxide surged in the atmosphere, trapping heat. Ice-free poles meant there were no ice's major reflectors to bounce sunlight back into space. Global temperatures began to climb again. Sea levels rose. Tropical storms became more violent. This yo-yo of cooling and heating created environmental whiplash. Entire species evolved to handle heat, and were then wiped out when the world went cold. Others thrived in cooler climates, only to be pushed to extinction when temperatures soared. Water itself was extreme. In some regions, flooding was constant. Rivers overflowed with every monsoon, spreading nutrient-rich sediment, but also drowning nesting grounds. Elsewhere, drought stretched for months. Lakes dried to cracked mudflats. Plants withered. Herds moved or died. Fresh water became one of the most precious resources in these cycles. Dinosaurs that could travel long distances or tolerate thirst had an edge. Others clustered around permanent water sources, competing fiercely for territory. Fire, too, was a frequent visitor. In dry seasons, wildfires swept through fern prairies and conifer forests. Lightning strikes ignited acres of dry vegetation. For many species, fire was a threat. For others, it was opportunity. Some plants evolved to regrow quickly after a burn. Others used fire to spread seeds. Herbivores returned to scorched fields for the new growth that followed. The dinosaurs didn't fight the fire. They learned to live with it. These environmental extremes shaped more than survival. They shaped behavior, biology, and movement. Species that once stayed in one place became migratory. Those that once relied on a single food source broadened their diets. Some began nesting in more protected areas. Others evolved traits like longer limbs or larger lungs to move farther and faster in search of safety. These were not optional changes. They were the cost of existence. Temperature swings influenced physical traits. In warmer climates, dinosaurs developed larger surface areas to dissipate heat, longer tails, wider frills, thinner bodies. In cooler zones, some developed insulation. The first feather-like structures may have emerged not for flight, but for warmth. Small theropods living in variable climates needed to retain heat. Their bodies responded with simple filaments, a primitive form of what would later become feathers. These adaptations show how temperature shaped not just behavior, but the very form of life. Some species learned to take advantage of extremes. Pterosaurs used rising heat columns over hot terrain to soar for hours without flapping. Aquatic reptiles timed reproduction with seasonal floods, letting their young grow in temporary wetlands before the dry season returned. Early mammals foraged at night to avoid daytime heat and predation. Even insects evolved to hatch during specific weather windows, taking advantage of brief periods of rain or warmth. The entire ecosystem began to operate on cycles of boom and bust, of abundance and scarcity. These extremes also carved the planet's future. Erosion from heavy rains cut deep canyons. Ancient lava flows redirected rivers. Shifting climate zones pushed forests northward and drove deserts into once fertile land. And through it all, dinosaurs moved. They didn't conquer the land by brute force. They followed it, watched it, remembered it. They returned to nesting sites that had survived past floods. They avoided volcanoes that had burned generations before. Their survival was tied not just to instinct, but to a growing awareness of the patterns in their world. Fossils tell us this story not in words, but in layers. Alternating bands of volcanic ash and lake sediment, tree trunks petrified where they stood, preserved by sudden lava flows. Bones found in clusters, indicating a herd that died together in a sudden flood. Ripple marks in stone, left by drying ponds after a drought. These details speak of a planet constantly in motion, not only physically, but ecologically. A world of extremes does not favor the strongest, it favors the most adaptable. In the Jurassic, this meant constant change. It meant creatures who could move, grow, respond, who could survive not just in abundance, but in absence. The dinosaurs that thrived here did so because they lived in the rhythm of the extremes. They did not resist the chaos. They became part of it. And in doing so, they rose to become the most successful land animals Earth had ever seen. They had survived extinction, conquered extremes, and learned to adapt to fire, flood, and famine. Now, with the world reshaped and the stage cleared of their ancient competitors, the dinosaurs began to diversify in every direction. This was not just growth, it was an evolutionary explosion. A sudden global radiation of forms, sizes, behaviors, and strategies. They did not simply fill niches left behind, they created entirely new ones. This was the Dinosaur Explosion. It began quietly at first. In the early Jurassic, the dinosaurs were already spreading. Their numbers were rising, their bodies becoming more specialized. But as Pangaea continued to fracture and climates became more regionally stable, something changed. Isolated populations began evolving in different directions. What had once been a mostly uniform group of reptiles began to split into lineages that would shape the rest of the Mesozoic. Theropods, the bipedal predators, diversified into both large and small forms. Some grew longer jaws and thicker necks for taking down large prey. Others became more gracile, with lightweight frames and longer arms for chasing smaller, faster animals. In different corners of the world, distinct branches began to appear. Megalosaurs, ceratosaurs, and early allosaurs all took root in this time, laying the foundation for the apex hunters that would follow. And below them, even smaller forms emerged. Quick-footed insectivores and opportunists that hunted in the undergrowth, scavenged carcasses, or preyed on eggs and hatchlings. Sauropodomorphs, once slow, modest-sized herbivores, underwent dramatic changes. Some began to grow at astonishing rates, their bodies stretching out into the immense, four-legged giants that would dominate the Jurassic world. Their necks lengthened, vertebrae expanded, and legs thickened into pillars. Sauropods like Cetiosaurus and Mamenchisaurus appeared in Africa and Asia, each pushing the limits of size and reach. As their bodies transformed, so did their feeding strategies. Some specialized in high browsing. Others swept their necks side to side, grazing low vegetation. Their stomachs adapted to handle huge volumes of plant matter, and their lungs evolved to support their massive frames. Ornithischians, the bird-hipped dinosaurs, began their own quiet revolution. Once small and unassuming, they now branched into many forms. Heterodontosaurs developed distinct tooth types for different feeding styles. Early stegosaurs appeared, their backs lined with plates and tails armed with spikes. Ankylosaurs began developing armor across their bodies, a response to growing predation. These herbivores were not just prey. They were problem solvers, defenders, and survivors in a dangerous world. This explosion of diversity wasn't just biological, it was ecological. Dinosaurs began occupying every role in the ecosystem. They grazed in open fern prairies, they browsed in dense forests. They hunted on riverbanks and in dry uplands. They nested in colonies, roamed in herds, and fought for dominance. They shaped the land not just by their presence, but by their interactions. Predators regulated herbivore populations. Herbivores shaped vegetation. Their movement patterns influenced plant distribution. Their feeding strategies opened space for new plants to evolve. The ecosystem became a web of connections, and dinosaurs were at its center. The spread of dinosaurs across the globe was also accelerating. As the continents drifted apart, species found themselves cut off from old populations and exposed to new environments. This geographic isolation led to speciation, the formation of new species as groups adapted to local conditions. In North America, certain sauropods developed broader bodies to support different feeding angles. In Europe, some theropods adapted to forested environments, growing shorter and more agile. In Asia, ankylosaurs developed dense armor and tail clubs to defend against more agile predators. This was not a single explosion. It was thousands of localized explosions, each shaped by geography, climate, and time. Even reproductive strategies were evolving. Nesting behaviors became more diverse. Some dinosaurs laid eggs in open sand pits, others built mounds. Still others used communal nesting grounds. Clutch sizes varied. Incubation times changed. Young dinosaurs began to show signs of staying with their parents for longer periods. Fossil evidence from certain sites shows adults near hatchlings, suggesting the emergence of care beyond egg-laying. This shift in reproductive behavior helped ensure survival in unpredictable environments, especially where predators constantly patrol. New behaviors evolved alongside new forms. Dinosaurs began displaying more complex social dynamics. Trackways suggest herds moving in coordinated patterns, likely with dominant individuals guiding the group. Some species may have had vocal calls for communication, warning of predators or signaling group movement. Others may have used body language, postures, frills, or tail positions to express aggression, attraction, or submission. Crests and horns were not just for defense. They may have served as visual signals, evolving for display as much as survival. As dinosaur diversity grew, so did the complexity of their environments. Forests became more layered, wetlands expanded, new plant types evolved, responding to heavy grazing and browsing. Pressure cycads and ginkgos spread. Horsetails and ferns rebounded after seasonal fire. Conifer forests adapted to shade and competition. Entire ecosystems were now cycling around the movements of dinosaurs. This explosion also laid the groundwork for future innovation. Feathers, which likely began as insulation in small theropods, may have started to diversify during this period. Though still primitive, these structures could have served multiple roles, regulating body temperature, aiding in display, or even improving balance during movement. The early steps toward flight were beginning to form, quietly and without fanfare, in the shadows of larger dinosaurs. What made the dinosaur explosion so remarkable was its scale and speed. Within just a few tens of millions of years, a blink in geological time, dinosaurs went from a few adaptable survivors to the most dominant land animals on the planet. They didn't just outlive their competitors, they replaced them. They changed the very rules of life on Earth. And this was only the beginning. The Earth was no longer a single broken continent drifting apart. It was becoming something new, a world of rich ecosystems, diverse landscapes, and endless evolutionary potential. The explosion of dinosaur diversity had reshaped life across the planet, but it was only a preview. The creatures that now roamed every corner of the Jurassic world were marching towards something even greater. This was the lead-up to the golden age of dinosaurs, a time when their dominance would reach its peak, and their influence would extend from the soil beneath their feet to the skies above. In the final stages of the early Jurassic and the beginning of the Middle Jurassic, the planet was stabilizing. The massive volcanic eruptions that had shattered Pangaea and driven climate chaos were finally slowing. Sea levels began to rise steadily, carving new coastlines and feeding wetland ecosystems. Rainfall patterns became more predictable. The relentless extremes that had tested every life form were softening into rhythms that favored growth, expansion, and specialization. It was in this window of calm that the dinosaurs began to flourish like never before. Sauropods, already enormous, began to dominate entire continents. Their bodies evolved into more efficient engines of herbivory. Their legs became thicker, more columnar. Their vertebrae developed air sacs to reduce weight while maintaining strength. Their tails, once merely for balance, became tools for defense, for communication, and possibly for coordination during migration. Species like Cetiosaurus and Shunosaurus traveled in vast herds, eating constantly as they crossed floodplains and forests, leaving behind trails of flattened vegetation and fertilized ground. The presence of these massive animals had profound ecological impacts. The plants they consumed had to evolve or vanish. Some developed tougher leaves, others grew faster to recover from grazing. Their movements opened forests, allowing sunlight to reach the ground and encouraging new growth. Their dung enriched the soil. Entire ecosystems, from beetles to birds, depended on the wake of the sauropod. They were no longer just participants in the ecosystem. They were shaping it. Predators responded to this new abundance. Megalosaurs, ceratosaurs, and early allosaurs began to take form. They grew larger, stronger, and smarter, adapting to hunt juveniles or weakened adults. Their senses became sharper, their limbs more muscular. Some developed crests and horns for display or combat. Others refined their teeth and claws for gripping flesh. More efficiently, the age of specialization had arrived. No longer were predators just opportunistic hunters. They were evolving into apex tacticians, fine-tuned to take on the growing challenge of a world ruled by giants. Herbivores other than sauropods also evolved rapidly. Stegosaurs, with their backplates and spiked tails, began to thrive in forested regions, using their unique features for both defense and thermoregulation. Armored ankylosaurs started to appear, their bodies turning into living fortresses. Small bipedal ornithopods evolved longer legs and better coordination, allowing them to outrun predators in open terrain. Each of these groups filled new ecological roles. ensuring that no part of the food chain was left unclaimed. Beneath their feet, the first true mammals quietly continued their own story. Though still small and nocturnal, they were diversifying too, feeding on insects, hiding in burrows, climbing trees, and adapting to the edges of ecosystems where dinosaurs could not reach. Their presence was subtle but important. They were the silent witnesses of the Golden Age, waiting for a time of their own. In the skies, the evolution of pterosaurs was picking up speed. Once awkward gliders, they had become powerful flyers. Species like Dimorphodon and Rhamphorhynchus soared over coastlines, feeding on fish and insects, nesting in cliffs and high branches. Their wings, formed from elongated fingers and stretched membrane, were engineering marvels. Their hollow bones gave them the strength to lift off and the lightness to ride thermals for miles. Some began to show signs of social behavior, nesting in colonies or displaying crests for communication. They were the first vertebrates to truly master the air, setting the stage for what would one day become bird-like flight. As the continents continued to drift, the dinosaurs followed. They crossed newly formed land bridges. They adapted to island environments. They tracked rivers that wound between mountains and valleys. Each new terrain offered challenges, and every challenge led to new forms. Isolation caused speciation. Environmental pressure drove innovation. The result was a steady march toward complexity. This time of stability allowed for another important shift: the development of long-term ecosystems. Instead of collapsing under constant stress, food webs began to stabilize. Prey and predator populations cycled in balance. Seasonal plant growth returned like clockwork. Nesting patterns became predictable. Migration routes were passed down. And with this new rhythm came evolutionary confidence. Dinosaurs could afford to grow larger, invest in parenting, experiment with display, and expand their territory. The age of experimentation was giving way to the age of mastery. Even the climate seemed to support this new order. Global temperatures remained high but consistent. Tropical zones stretched far into the continents. Ice was almost non-existent at the poles. Lush forests blanketed much of the land. Shallow seas teemed with marine reptiles. Oxygen levels remained high enough to support massive animals and active metabolisms. It was a world built for life at scale, and the dinosaurs rose to meet it. But this calm would not last forever. Earth was always shifting, always preparing its next test. The Middle Jurassic was only a prelude to what was coming. In the late Jurassic, sauropods would reach their full potential. Allosaurs would dominate the apex. Feathered theropods would begin to leap toward flight. Stegosaurus would wield its plated armor like a living shield. Ecosystems would stretch across every corner of the globe, from polar forests to tropical swamps. The Golden Age was almost here. Towards the Golden Age, the story of the dinosaurs became a symphony, each group playing its own part in a world of motion, color, sound, and power. They had emerged from the shadow of extinction. They had conquered the chaos of volcanoes and the violence of shifting continents. And now, with the planet at peace, for a moment, they were ready to rise to their greatest heights. The Golden Age of dinosaurs was not a distant dream. It was just beyond the horizon, and they were already walking toward it.